I'd like to start by acknowledging the input of my co-authors, Ben Hayes and Mike Goddard, and I'll be talking to you about genotyping dairy females. So I think there's two main aspects that we can benefit from genotyping females, one of which is a sort of national benefit, which is improving the reliability of genomic selection, and the second, of course, is what the farmers can get out of it. So you've got the national good versus the actual farmer profitability aspect. So the farmers can obviously get benefits from identifying elite females or males, identifying the best heifers to become replacements, getting certainty of parentage, avoiding inbreeding, and avoiding genetic defects. And I will cover those a bit later. So the first part of my talk, I'm going to talk about contribution of females to the reference population. So the issue here is that as genomic selection replaces progeny testing, there's a risk that the reliability of genomic breeding values will decrease. And this is obviously because we don't have so many bulls that are being progeny tested and adding to the reference population. The issue is that the distance between the reference and the predictor population increases, and we suspect that this is probably a bigger risk for small populations or small reference populations. So how can we reduce the deterioration in reliability? Well, of course, exchanging genotypes, while there are still genotypes to exchange, is one strategy. Using denser SNP chips and better statistical tools can possibly give us another way of avoiding this deterioration. And the third aspect, and what I'm going to talk about, is genotyping females as well. So in order to include females in the reference population, we think that you need to be a little bit cautious in the way that you do this because of preferential treatment. So obviously if you have the very elite females, then there is a risk in some circumstances that those cows may have been preferentially treated in some way. So they may have been fed a little bit extra and so on. So we prefer the strategy of taking a more random approach in terms of selecting those females. Having said that, we haven't been entirely random about the way that we select those females. We have a project which is called the 10,000 Holstein Cow Project, where we've identified cows that have excellent records. And by that, I mean completeness of records. So we're looking for ones that have got a complete set of fertility, survival, and production records. So we actually developed a sort of scoring system to identify those cows and identified the ones that had the highest scores across Australia. So we weren't necessarily picking entire herds, but we were cherry picking the cows in those herds that had the best records for our purpose. So we worked very closely with Holstein Australia to make this logistically feasible. We were visiting a lot of herds, collecting a lot of tail hair samples. And there were examples of myself, Ben Hayes, the rest of our group, going out and basically pulling the tail hairs ourselves. So we've been pretty practical in terms of our approach to this project. We've worked with ADHIS, Australian Dairy Herd Improvement Scheme, to actually implement this into the genetic evaluation system and work on the quality control. And the idea is obviously to improve the reliability of the genomic breeding value, as we call them in Australia, ABVs, Australian breeding values, to a level approaching that of the proven bull. So what we did, we collected samples from just over 10,000 cows. We genotyped them for the Illumina 50K SNP chip. And out of these, 9,900 passed the quality control that we set in place at ADHIS. We had to update the ADHIS system to actually handle cows in the reference population. And we've also obviously done quality checks to assess the impact on the reliabilities of young bulls. The farmers, of course, wanted to get the genomic breeding values themselves, so this is part of the task that we've set ourselves. We haven't left the Jersey population out. We've also run a project where we've genotyped 4,000 Jersey cows, identified them in a similar way to the Holstein project. We've got excellent herd recording data, and the idea is to increase the reliability of Jersey genomic breeding values. Again, we worked really closely with the Breed Society to make this happen, and the Jersey Association were very active in terms of their participation. So we collected 3,900 samples, genotyped them, and used the same pipeline as the Holsteins. So in terms of the Australian animals that we have in our reference population, we have 12,649 Holsteins, of which around 10,000 are females, and 5,200 Jerseys. Now, in a nutshell, this has had a positive effect on the reliability of our bull proofs. It's added 4 to 8%. In this table here, this is a sort of breakdown of the reliabilities in a test set of 437 young bulls. So for the production traits, when we have a reference population of just bulls, the reliability was 54%, and adding cows into that reference population increased the reliability to 61%, so it added 7%. It was even higher for cell count and not quite so good for fertility, but that could have been the way in which we were actually selecting those cows in the first place. So another thing that we intend to do with this data is to incorporate it with the 1,000 Bull Genomes project. So through the global effort of genotyping 1,000 bulls, we're intending to impute up the 50K that we have on these 10,000 cows up to sequence, and just to see what impact that will have on the reliability. Obviously, as Bevan said, the reason why we're interested in this is because the causative mutations are in the data set, and you no longer have to rely on LD with SNPs. And we're hoping that this will give us a higher accuracy of prediction and also a better persistency of accuracy across generations. And again, I mean, the proof will be in the pudding. We don't know this yet, but we're hoping that it'll give us a better prediction across breeds. So the second part of my talk is how dairy farmers can make use of this technology. And I wanted to look at the question, the slightly controversial question, I guess, of how much farmers can afford to pay for genotyping. So I'm just going to focus on what the commercial dairy farmer can get out of this in terms of selecting replacements, using mating plans to control inbreeding, and achieving certainty of parentage. Of course, avoiding genetic defects and selling pedigree heifers at a premium is also equally valuable avenues of revenue, but I haven't covered them in this talk. So for replacement heifers, I assume genotyping using the Illumina low-density SNP chip, and it's based on keeping the best heifers as replacements. So reliability of parent average 30%, of genomic breeding values of 60%, and being an island, I've used assumptions that are associated with the Irish Selection Index, EBI, and also the cost of the SNP chip in Ireland, which is €29. I ran two scenarios, one where selection on parent average is not possible, and the other where you use genomic breeding values instead of parent average. So in a very optimistic scenario where you have 40 heifer calves for 100 cows in your herd, which I admit is slightly on the optimistic side given low fertility levels, a farmer may have an opportunity to select 20 of the best replacements and sell 20 of the worst. So under this scenario, if you ignore parent average, the benefit of genotyping, i.e. after accounting for the cost of the SNP chip, is €46. But if you include parent average, then to use this technology just for selecting replacements, I think the cost of the chip needs to be about €15. However, you can obviously get further benefit from the chip by including other aspects of, or other ways of using the technology. So one way in which you can do this is through mating plans. Obviously, having the genomic relationship between animals is a much better way of estimating co-ancestry than using pedigree relationships. And this graph just shows the, I suppose, the range of, or the distribution that you have in those genomic relationships compared to the pedigree relationships. So I presented this in a little bit more detail in my talk on Monday, but basically the benefits of using genomics compared to pedigree is worth around about $50, that's 50 US or 50 Australian, or 39 euros. There's also a benefit in terms of pedigree verification, and for seasonal systems such as Australia, New Zealand, Ireland, this is especially useful when you've got a lot of cows calving at the same time, and it's difficult to actually work out whether the calf that's been born is from a variety of different dams. Ben has shown that it's possible to work out the sire unambiguously with a reasonably small number of SNPs. And in Australia, this is worth the equivalent of around about 28 euros, being able to unambiguously work out parentage. So I've just done some, I suppose, quick calculations on what it would be worth at a 29 euro test. And obviously, with selecting the best replacements, just using pedigree information is actually better right now than genotyping. But if you add in all the other benefits that come from this, then I would argue that there is a benefit, an overall benefit in using genotyping that's currently available to the dairy farmer. And I think that as genotyping actually falls in cost, then it's going to be increasingly more attractive for farmers to use this. So, just to conclude, there's two parts to my talk. The first is that adding females to the reference population increases the reliability. In Australia, we've shown that this is up to 8%. And genotyping in females is profitable at 29 euros, but I think it really will fly as soon as that cost gets to around about the 15 euro level. And with that, thank you very much.